We have two speakers tonight. Our first speaker is Dr. Graham Cooley of ITM Power, who has been CEO of that company since 2009. He has a PhD in physics, an MBA, and is a fellow of the Institute of Metals, Minerals and Mining, IO3M. He has been working in the power sector since 1989 and is a member of the UK government's Hydrogen Advisory Council. Graham will discuss the market for green hydrogen as a net zero fuel and how it's being produced by the electrolysis of water. ITM Power is now delivering projects from the world's largest electrolyser factory with a capacity of 1 gigawatt capacity per annum, located in Sheffield. Generation of hydrogen by electrolysis is presented, including some key international projects. The presentation will discuss the use of hydrogen to replace grey industrial hydrogen at refineries and for other industrial processes. Our second speaker is Dr. Chris Manson-Whitton, who is a director of Progressive Energy and an expert in low carbon energy. He's a member of the Arms Braziers. He formulated the HyDeploy project with Cadent and Northern Gas Networks and is managing the delivery of that project, which is injecting 20% hydrogen into parts of the existing gas system. Chris will tell us about the HyNet Northwest project being delivered by Progressive Energy and Cadent, which is going to produce, distribute and store low carbon hydrogen for use in industry, heating and transport. Carbon dioxide from the production of hydrogen from natural gas will be captured and stored in depleted gas reservoirs in Liverpool Bay. More hydrogen, not carbon, and here is my name and the two other speakers. The need for more hydrogen, less carbon, is to reduce emissions of greenhouse gas, of which over half of UK's emissions come from industry, residential and transport. The map of the UK shows 6 industrial clusters, which between them emit 38 million tonnes of carbon dioxide per year. That's 8 or 9% of UK's total. Cleaning up those emissions and replacing natural gas with hydrogen as a fuel will require new process infrastructure, which we're about to hear about. This picture here shows the north of England, from the Mersey down here up to the Humber and up to Tees and Tyne, with Liverpool and Manchester in the foreground, Leeds and its environs somewhere in the middle distance, and Hull and Newcastle in the far distance. Much careful study and trials have gone into studies leading to the use of 20% blend of hydrogen and natural gas, and then after more careful trials to 100% hydrogen. And the green line here is a potential pipeline route through the whole massive conurbation. Thirdly, on transport, hydrogen is an alternative to batteries for transport, including buses, cars, and other road vehicles and trains. These 3 pictures show a hydrogen bus, the schematic of a hydrogen-powered car, and a tube trailer to transport hydrogen. Hydrogen-powered trains are arriving from Alstom and the association from the University of Birmingham with rolling stock supplier Porterbrook. The tube trailer is for North American roads. It's larger than perhaps we'd have normally in this country. And at a pressure of 250 bar, it only carries 550 kilograms of hydrogen, enough perhaps 14 cars to 140 cars to refill. Hydrogen is a very light gas. The single-decker bus has its hydrogen tanks on its roof, so any hydrogen escape would vent upwards safely. Double-decker hydrogen buses are now being built by Wright Bus in Northern Ireland for use in Aberdeen, Birmingham, Liverpool and London. The hydrogen-powered car is shown as a schematic. As to date, very few have appeared on UK roads, and we still have only a limited number of filling stations. So many potential uses for hydrogen. Now to tonight's speakers who have experience of real projects, and we'll take questions after both presentations. So firstly, to Dr. Graham Cooley.
So yeah, thank you very much for your introduction. I'm going to talk you through green hydrogen and ITM Power. So ITM Power was the first hydrogen and fuel cell related company on the London stock market. We're a manufacturer of electrolysis equipment. So we're actually a relatively unusual company for the AIM market. We're an engineering company and we're a manufacturing company from the north of England. An electrolyzer then is a device that takes in water and electricity and splits it into hydrogen and oxygen. And if you use renewable power to split the water into hydrogen and oxygen, you make a net zero fuel. Actually, it's the only known fuel with no carbon in the entire supply chain. You make it with renewable power, and you split water. You also make oxygen, which is very interesting as well, because not only is it net zero in terms of CO2, but it also makes its own oxidant. So it's the only fuel that does not deplete atmospheric oxygen. And it also does a third and very important thing. You can use it to store electrons. So my background was in the power industry. I was development manager at National Power, which is the UK's largest power generator. We developed Regenesis, which at the time was the world's largest electrochemical energy store. We built 100 megawatt hours at Little Barford. And I can tell you, having spent a career in energy storage, that electrons are very difficult to store for long periods of time. And the best way of storing electrons in massive volume for very long periods of time is to turn electrons into molecules, because it's easy to store a molecule. You can put them in a tank or put them in a gas grid. And actually, one of the key applications is to store excess renewable power as hydrogen molecules and put them in the gas grid to decarbonize heat. You can also use them for transport, and you can also use them for decarbonizing what I've called chemistry. Actually, what that means is refineries, ammonia, methanol, and metals production. So some people that I have met seem to think that we have to create a market for hydrogen and that a market doesn't exist. We use 70 million tons of hydrogen per year in industry. It's used to make ammonia, it's used for refining, and it's used for producing methanol, which is the building block of all chemistry. And all of it needs decarbonizing. And if the world is to get to net zero, we have to decarbonize all of that hydrogen in 29 years. And not only that, we have to eliminate natural gas from the gas network. We have 29 years to do it. And you have one net zero energy gas available. It's green hydrogen. Some key achievements that we made over the last 6 months. We now have a record backlog of projects, 124 million pounds worth of projects. We tendered over the last 12 months, 435 million pounds worth of capital equipment, alongside Linde Engineering. Linde Engineering are our strategic investor, and we have a joint venture with Linde called ITM Linde Electrolysis to supply the world with green hydrogen and electrolyzer systems. They're also a strategic investor in ITM Power. In October, we raised 172 million on the London stock market, and we got a strategic investment from Snam. Snam are the world's second largest gas transmission company. Actually, Gazprom is the only other larger gas company. 172 million. We were 2.5 times oversubscribed. the City of London offered us £0.4 billion and are incredibly well informed about the energy transition, about energy storage, and about electrolysis equipment. First Monday of the new year, we moved into the world's largest electrolyser factory. It's on Shepcote Lane, Brightside, Sheffield. It's on the old British Steel stainless steel site, 134,000 square feet, and all of the company now under one roof. We sold 24 megawatt electrolyser to Linde at Leuna, and that goes into the existing hydrogen pipeline at the Leuna Chemical Works, and the hydrogen is being used by Total, the oil and gas company. We've just concluded the front-end engineering design study of 100 megawatts in Humberside. That will connect directly with Hornsea 2, which is a 1.4 gigawatt offshore wind farm. It's actually the world's largest offshore wind farm. And the hydrogen goes directly into the Phillips 66 refinery on the Humberside. And we got the announcement from Shell that they're increasing the Refine project. We built 10 megawatts at the Shell Vesseling refinery, and they are now working with us to deploy a further 100 megawatts at the refinery. And we have a strategic partnership with Scottish Power in Scotland, who are part of the Iberdrola group. And we've just applied for planning permission for a 20 megawatts at the Whiteley wind farm, which is the UK's largest onshore wind farm. So some significant progress over the last few months. Why green hydrogen and why now? The cost of green hydrogen is dominated by the cost of renewable power. And renewable power has come down in cost radically. And so the cost of green hydrogen has now come down. And I'll show you at the end what the costs look like. As you deploy more and more renewable power, of course, you need more and more energy storage. And the world is also moving to net zero targets. So you have three very powerful things that have come together. Reduction in the cost of green hydrogen and electrolysis, increase in the demand, and also the policy of moving to net zero, with green hydrogen as the only net zero energy gas. And the amount of funding coming forward now for green hydrogen is very significant. So you'll know that the EU Green Transformation Package was €1 trillion. The US one is $2 trillion. €1 trillion, 15% of it is allocated to green hydrogen, not hydrogen, green hydrogen. And 100 billion, 10 billion a year for 10 years for contracts for different auctions for green hydrogen. And all over Europe and the rest of the world, announcements of electrolyser targets in the gigawatts of size. So gigawatts of electrolysis to achieve the energy transition. In the UK, we've announced 5 gigawatts. The difference with the UK target is that the UK haven't yet been explicit about how much of it is green hydrogen and how much of it is blue hydrogen. But we work very closely with Shell and Linde and Snam and Ørsted and Iberdrola. And we manufacture in the UK. And as I said, our target market is replacing grey hydrogen for industry with green hydrogen. And today that market is 70 million tonnes per annum, which is equivalent to 600 gigawatts of electrolysis. That is an astonishingly large number. That is, in revenue terms, in the trillions. It is a massive market. We've been on an amazing journey at ITM. I started in 2009. In 2011, we launched our first product. We got the factory ISO accredited, and we got the first 10 kilowatt product CE marked. And we launched it at Hanover in 2011, and it was 10 kilowatts in size, the size of a camping fridge. Okay, this year we delivered 10 megawatts to the Rhineland refinery. So that's a scale up of 3 orders of magnitude, or 1,000 in a decade. And in fact, we're now bidding 100 megawatt plants on a very regular basis, which is the next order of magnitude scale up. This is our product. They are electrolyzer modules. These are the modules that take in water and electricity, and they make hydrogen. They make hydrogen at either 20 or 30 bar, and the differential pressure. What you see is a laminated stack of electrodes, membranes, and catalysts that splits the water into hydrogen and oxygen. Okay, the stacks rapidly respond. You can turn the stack off and on in less than a second. So if you know anything about generating pressure at 30 bar, 1 second to turn off and turn on, because they float on hydraulics, which you can see at the bottom. So not only is it a very elegant piece of electrochemistry, but it's also a very elegant mechanical hydraulic design, so it can be rapidly cycled. And the reason that you need to turn them on and off rapidly is so you can use them to balance the grid. They are a flexible, rapid response load. Okay, now those 5 megawatt units, we are pre-engineering 20 megawatt packages. And that's being done with Linde Engineering in Dresden. Why do we pre-engineer 20 megawatt packages? Well, in a word, non-recurring engineering cost, which is actually 3 words. We are pre-engineer to standardize the balance of plant and to drive out costs in the balance of plant. So that pre-engineering allows us as well to minimize the amount of on-site work and to rapidly deploy. This is what a full system looks like. This is a power system, a control system, a water system, and a gas system. It's 100 megawatt output of a front-end engineering design study. We partnered with Linde Engineering because they are the world's largest deployer of grey hydrogen in industry, and they are Linde Engineering is the largest EPC contractor, 80,000 employees. They now have a capitalization just in excess of Shell. So a very large and important German engineering company. The deployment at Leuna, fabulous for us. We went through a competitive tender, and we beat in Germany, in the heartland of the German chemicals industry. We beat all of the competitors, including the German electrolyzer companies. Linde Gas owned the pipeline, and it's a grey hydrogen pipeline, and we are supplying green hydrogen. The first step is 24 megawatts, and there's ample possibility of scaling up the electrolysis. A great reference plant for us in Germany and in the chemicals industry. The Rhineland refinery. So the Rhineland refinery is Shell's flagship refinery in Cologne, in Germany. They are developing it as their first e-refinery. In other words, what we will be doing there is making synthetic kerosene or sustainable aviation fuel. We delivered the first 10 megawatts to the Rhineland refinery. Just for sizing, 10 megawatts makes 1% of the hydrogen used at the refinery. So to completely decarbonize all of the grey hydrogen at the refinery, by the way, grey hydrogen is hydrogen made from natural gas and steam methane reforming. To decarbonize all of that grey hydrogen, the refinery would need 1 gigawatt of electrolysis. So we're expanding by 100 megawatts. We did the full EPC. on the 10 megawatts, and we're delighted to get the result from Shell that they wanted to expand by a factor of 11, actually add 100 megawatts, and we're doing that jointly with Linde Engineering. So very important. Now, just to point out, I've now mentioned to you 3 oil and gas companies. Phillips 66 in the Humberside, Total in Leuna, and Shell in Cologne. Why it is important to decarbonise hydrogen at refineries? Answer: all refineries in Europe are included in the Renewable Energy Directive, and they have an obligation to make 14% of all of their products renewably in the next 10 years. Okay, an amazing driving force for the adoption of green hydrogen and electrolysis at refineries. This is our factory. If you happen to be traveling up and down the M1, you'll see it off the M1. In fact, the M1 to me now goes Outokumpu, ITM Power, Meadow Hall. They're the 3 big buildings you see as you go along the M1. 134,000 square feet. We moved in, we're shipping from the factory. We raised enough money in the funding round to build to inventory so we could halve our lead times, and also build a second gigafactory of 1.5 gigawatts in size, an additional 1.5 gigawatts when this gets to 60% capacity. The factory contains our test centre and our R&D centre. It contains the world's largest ATEX zone for testing electrolysis equipment indoors. We have a 5 megawatt power supply. All of our electrolyzers in the field are connected to our control room via a SCADA system, and we monitor every one of our installations in the field. So all the pumps and solenoids and valves and alarms are all monitored 24 hours a day by 2 engineers. And we offer that after-sales support service to our customers. All of the data goes into RAMS modeling. So we use reliability, availability, and maintainability software so that we can optimize operating points. It is an electrochemical device, not a rotating machine, but actually operating points, again, are very important in terms of the compromise between total cost of ownership, performance, and lifetime. Cost reduction is very, very important for us. We are driving towards cost reduction with manufacturing volume, semi-automation, and procurement. And we have a very aggressive cost reduction curve that we publish, actually. It goes out on the London stock market, and we are tracking ahead of our cost reduction. Cost reduction, important for market share. Not so important for the cost of hydrogen, and that's a very, very common mistake. So how much does hydrogen cost? So this is the McKinsey model for costing hydrogen. The dark green color is the cost of natural gas, and that's the equivalent cost in Europe. Lighter green is the cost of grey hydrogen, and that grey hydrogen is the hydrogen that I told you had a market of 600 gigawatts of electrolysis. And then the lightest green is for blue hydrogen. So assumptions. First of all, the cost of green hydrogen is dominated by 2 things: by the cost of the renewable power and its load factor, and then by the capital cost of the electrolyzer. So at €500,000 per megawatt, at 50% load factor, and at 5 cents or 4 pence per kilowatt hour, hydrogen comes out at $3.2 a kilogram, which is cost comparable with blue hydrogen in the UK. You get to 2 cents per kilowatt hour, and you're cost competitive with natural gas in parts of Europe. And anywhere in between, you're cost comparable with grey hydrogen. So you don't need to believe me. you can read Bloomberg New Energy Finance or Platts, Hydrogen Council or Hydrogen Europe. Between 2020, the mid-2020s and 2030, hydrogen at $1.6 a kilogram. And from 2030 to 2050, hydrogen at $0.8 a kilogram, which is equivalent to natural gas at between $6 and $12 per MMBTU. And it is net zero. So one last slide, which is about the 10-point plan, Boris's 10-point plan. Was delighted to see the 10-point plan. There are actually 5 points relevant to hydrogen. Point number 1, 40 gigawatts of offshore wind by 2030. That's in a decade. You're going to need a lot of energy storage. Actually, our instantaneous power peak in the UK is about 50 gigawatts. And so consequently, we are planting up with an excess of our instantaneous peak so that we can use some of the excess to make hydrogen to decarbonize industry. 5 gigawatts of hydrogen, point number 2. Point number 5, low carbon buses. There are actually 3 manufacturers in the UK of fuel cell buses. They are Wrightbus, Optare, and ADL in Scotland. Sustainable shipping and aviation fuel. If you want renewable ammonia, and if you want renewable methanol, you start with green hydrogen. And then blue hydrogen and carbon capture and storage, which we'll hear more about from the next speaker. That was point number 8 in the plan. So a very, very significant amount of emphasis on hydrogen in Boris's 10-point plan, which I was delighted to see. So thanks very much for listening, and I think we're taking the questions after the next speaker's presentation.
Thank you very much. It's a pleasure to be here and to speak to you. It's also a pleasure to see a few of my fellow armourers here as well, which is good. As the master introduced, I'm from a company called Progressive Energy. We've been going for around 22 years. And in fact, in 1998, we started working on low carbon hydrogen and carbon capture and storage. So we've been doing this for a long time. And our mission is to take material quantities out of our energy system. And what I want to do today is to give you a little bit of background of why and the context, look at some of those hydrogen market or those end user requirements, and then have a little look at some of those hydrogen markets. I will talk a bit about hydrogen production, but my main focus is on how we build the kind of infrastructure that allows us to beneficially use hydrogen across our energy system. This isn't a form of extreme social distancing. This is actually my youngest daughter who was bungee jumping at the time. But the point I wanted to make is that by the time we get to 2050, she will still be younger than I am today. So the decisions that we are making together are creating the world that she will be living in a very short space of time. And that really does condition certainly my view, and I know many of our views, as to the importance of what we're doing here. Another graph which I found particularly sobering is one here on the left from Neil Kay from the Met Office. It looks at the proportion of fossil carbon emissions since we started emitting fossil carbon that have occurred in my lifetime. So if you look at this graph, I'm just a tickle over 45, and that means that 70% of the fossil emissions that have ever been emitted on this globe have happened in my lifetime. Even, one of my kids that's 15, a third of them have happened in their lifetime. Now that gives you an idea of how inexorably we have been emitting carbon. And that really does put the backdrop as to what we're doing. So then you take the picture in the middle. I mean, that's an image from the Committee on Climate Change's 6th carbon budget. And it kind of looks slightly benign, doesn't it? That 1990, this is UK emissions dropping down sort of a straight line-ish to 2018 and a sort of straight line to 2050. But when you look at what's actually been going on in terms of our overall emissions and the kind of inexorable rise in energy consumption we've had, you can see that this is a major issue to be solved. And again, an area that's very close to my heart, and I know is to Graham's as well, is actually our manufacturing and industry. And again, if we take that graph, this comes back from the Committee on Climate Change's Net Zero report in 2019. The red line is the one that we see and we're quite familiar with, and we've done really well in the UK. You know, we've gone from around 800 million tons of CO2 per annum to, you know, whatever it is, 430, 440 by the end of the graph that we've got here, which looks very good. The challenge is that's the emissions that comes from the stacks here in the UK. The blue line represents the emissions associated with the products that we use. And that is depressingly static. So you can see that actually up until the crash, we were rising inexorably. Then we hit 2008 and things dropped down. But pretty much you end up saying the needle hasn't really moved. And that's because we are still consuming. It's just quite a lot of it is happening offshore. Net zero means there is nowhere to hide. When we had an 80% carbon reduction, everybody thought they got the 20% of headroom. Net zero means we've ultimately got to get to net zero, and we'll need all solutions. So let me just rattle through 4 areas of demand where we need solutions. So industry. Why does industry need to tackle its carbon intensity? Well, there's a number of reasons. Industry genuinely, you know, and again, Graham's talked about the stock market, you know, corporate and social responsibility and the obligations of that means industry does need to do something. Customers are demanding products that are lower carbon, and ultimately there is an economic threat to our industry. The UK ETS opened today at £50 a tonne, and if people have been looking at the carbon pricing over the last decade, they will recognise that £50 a tonne is a huge price, and that is threatening that industry. And the risk is, if that industry can't pay for those emissions and closes down, we make our products elsewhere around the globe where they don't have to pay for carbon. And that actually represents a net challenge for our overall global emissions and loses the benefit to the UK in terms of our skills and economies that we could be using. So what are the solutions? Yes, we can be more energy efficient. Industry has tended to do that quite well. It is possible, and in some processes, in fact, the only way is to capture CO2 when it has been emitted, and particularly if there is chemical CO2 as an inherent part of the process, that can be the only way of doing it. Or when you're using energy in particular, switch to different fuels, to electricity, biomass or hydrogen. Now, there are challenges with all of them. We're going to focus on hydrogen, but there are those options. Domestic heat. This is probably the hardest and most challenging part of our energy system. The UK has historically focused entirely or almost entirely on tackling our electricity sector and hasn't recognised quite how much is emitted from our heating sector. This graph, which is now quite an old one, but a really quite powerful one, shows in red the half-an-hour demand of natural gas going into domestic heat in the UK. And that little grey squiggly line at the bottom is the fluctuation of electricity. So we talk about the electricity swinging enormously, but just see the swings both within day, both sort of week by week, and particularly seasonally in terms of our energy demand to that sector. That is a challenge to decarbonise. Making it even more challenging is that our housing stock is not well insulated, and that presents a challenge, recognising that 80% of the homes that will exist in 2050 already exist today. We can do great things with the 20% yet to be built, and we absolutely should do, but the challenge is we've got to deal with the types of property you already have. Energy efficiency is critical. Insulation, I've certainly done that here in my property. That's where I ended up putting my money. I couldn't change the heating system, but I could do something on the energy efficiency. Again, your options are you can switch to different fuels. Electric heat pumps, for example, could use biomass, and hydrogen is a potential. Dispatchable power. So we've seen this massive growth in renewables in the UK, fantastic progress. But again, as Graham hinted at earlier, how do we balance the system? How do we handle not only balancing the system we have today, but recognizing that passenger vehicles will end up with a big demand for electric, because we are going to see a lot of electric passenger vehicles, and we will see heat pumps in the heating sector as well. So actually our electricity demand, aside from anything else, could easily ramp, well, at a domestic level, could be doubling in terms of domestic electricity consumption, just from those two reasons alone, or indeed more. So what are the solutions? We can change and shift our demand patterns. We can store electricity. We can store hydrogen, and I will touch on that a bit later, as Graham has said, or we have generation that we can bring online rapidly. And again, that's what hydrogen allows us to do. And I will give you some examples of that later. And finally, mobility. You know, electric vehicles absolutely gaining traction for the passenger vehicle sector. I am sure we will see hydrogen vehicles in that sector as well, but there is no doubt the electric one, for that sector, electricity will play a big role. But as soon as you get to heavy goods vehicles, buses, trains, you need a solution that can give the range, the charge time, and everything else. Things we can do more on drop-in biofuels, increase the proportion. We can do substitute CNG, so bio CNG, so bio natural gas, using in trucks, and we're seeing that. And again, hydrogen is a possibility. I just want to put some kind of reality to what we're dealing with here, because I think it is important. I said we've made tremendous progress on renewables, and we have. But we just need to see it in context of the total UK energy consumption. So that's what this graph shows, what we use for electricity, where we get sort of some of the other, there are some other areas, there's sort of biomass going into certain areas as well, but got natural gas and we've got petroleum. When you put all that together, that is requiring over 1,700 terawatt hours of energy. And we've done really well on wind, and we're doing well on solar. And obviously we've had the benefits of nuclear too. We talk about the fact that we wish to be the Saudi Arabia of wind power, and we are well placed to do that. But just taking this data from 2019, in 2019, only 2% of the UK's total annual energy consumption came from offshore wind. And that was 10 gigawatts. So yes, we've got a fantastic opportunity to go up to 40 gigawatts on the offshore wind, and load factors are improving, so that will help. But that just puts into context that quadrupling of that still means that we're sitting very much on the left-hand end of that graph. Now, we have got some other low carbon renewables in there, but I have to say the offshore wind is the one that's going to see the big growth. There won't be a huge amount of solar or onshore wind going with it. It will be the offshore wind. That just gives you an idea of the challenge that we need to meet. And then similarly, the other challenge is, how do you manage things on a kind of day-by-day basis? And we've got the generation mix from March this year. And you can see at the beginning of the March, if you remember back, it was really windy. And so we were seeing sometimes, we topped 50% of our generation was coming from wind. Here I'm showing both on and offshore wind generation. But you'll have seen later on in March, there was a point where, quite frankly, there was no wind. We had a high, and less than 2% of our instantaneous electricity was being generated from on or offshore wind, and it was all being made up with gas. Just gives you an idea of the challenge we meet to meet net zero, is how do we deal with all of this? So what we will need is a suite of solutions. We will need more renewable electricity and electrification. There is a role for biomass. Absolutely, we need energy efficiency. We will need carbon capture and storage as part of our mix, and we will need hydrogen. It is not a competition. We need all of them operating together. So depends on whose view you take, whether you take Committee on Climate Change, National Grid's Future Energy Scenarios, others like Aurora or whatever. We need literally hundreds of terawatt hours of low carbon hydrogen. And to get to those sectors I've talked about, energy intensive industry, domestic heating, HGV, trains and buses, and then that flexible generation. So how are we going to get it? Well, Graham has obviously talked a lot about electrolysis, and I have had and operated one of his electrolyzer plants. I'll tell you a bit about the HyDeploy project a little bit later in the program, but there are other ways. So blue hydrogen, Graham has talked about, just alluded to. So this is where we take natural gas and we strip out the CO2, and then we permanently store that CO2, sequester that CO2, and then you have the hydrogen to deal with. And on the other side, you've got biohydrogen. So this is actually a project that we've been working with, which is looking to take waste resources to either a biomethane or into biohydrogen. And again, that's another way of producing. And we will need all three of these. The key factors will be the scale, how quickly we can build out to what we need, what the cost is, the maturity of the technology, the availability of the resource, and the carbon intensity. Now, Graham and I will have different views. I will put it absolutely clear here that by the time we get to 2050, we will need a substantial quantity of green hydrogen, and I would expect that to dominate the mix by 2050. On that journey to 2050, there is definitely a key role to get things moving, and over the next 20-30 years, where blue hydrogen will play a key role in heavy lifting at the kind of volumes we need in order to achieve the decarbonisation we need. And I'll tell you a bit about one of our projects a little bit later, but to show you how that fits and the kind of what we can achieve. What I really want to tell you about is how do we make this into a full energy system. So this is HyNet Northwest, which is a project that we conceived over 4 years ago. And I like to think of this as an energy ecosystem. The purpose of this, what we set out to achieve, was how do we take material quantities of carbon out of the Northwest region, a heavy industrial area of the country, densely populated, representing around 10% of the UK's population and a big chunk of its industry. How can we do that? And we were adamant 4 years ago that at the heart of that would be hydrogen. So this involves hydrogen, a hydrogen infrastructure that gets it from where it's produced, and it will be produced by multiple sources, to where those users lie. Now, to get that system going, to get the kind of volumes that we need, blue hydrogen is a key part of that. So for blue hydrogen, you need a way to store the CO2. So offshore in the Liverpool Bay, there are gas fields coming to the end of their economic life. They have been gas tight for millennia since they were formed, and they are now running out of natural gas. We are partnered with Eni, who are the Italian state oil and gas operator who own those fields, and they will be repurposed. So instead of natural gas coming offshore to onshore, it will be CO2 coming from onshore offshore. And most of that pipeline that you can see in orange also exists, and they've done all the work on repurposing the assets offshore as well as the pipeline. So then there is a short CO2 pipeline that takes us to where it says hydrogen production. It will be collecting CO2 from some industrial processes that currently emit CO2, but predominantly it will be from blue hydrogen production, where effectively we take natural gas, we strip the CO2 out, send that down the infrastructure, the CO2 infrastructure, and then we have a low carbon hydrogen we can use where we need to. And that goes into then the pipeline network, which is shown in black, which is a new distributed hydrogen system, an 80-kilometer hydrogen system that gets it from the source to the customers. Our initial facility is 350 megawatts. So that gives you an idea. Graham's been talking about his 10 megawatts rising to 100 megawatts. Our first line is going to be 350 megawatts of hydrogen production, and by 2030 we will be over 10 times that scale. So we'll be just under 4,000 megawatts of hydrogen production across 4 blue hydrogen facilities. That will actually enable us to deliver just under 50% of the region's natural gas use. So we'll be swapping out natural gas for low carbon blue hydrogen instead. Now, having done that, we've created the infrastructure, we've got the volumes at cost, and we are saving carbon today. But we would hope that infrastructure, it is designed so that other sources, bio-hydrogen sources, green hydrogen resources can link into that infrastructure, and we have a fully functioning market. The infrastructure also locks into storage, and I'll talk a little bit about that later. But I agree with Graham that, you know, you store molecules, not electrons, when you want volume, and that's what this will do. And then we will deliver to that suite of industrial users that I've talked about for dispatchable power and to link into the gas network for hydrogen blending. So let me just pick some of those areas out one by one. I won't spend too long. The carbon capture and storage side, I know our focus here is mainly hydrogen, but this is just demonstrating the deliverability of what we'll be able to do on that. You know, currently there are over 20 projects around the globe storing CO2, just like we will be doing here, making sure that we can decarbonize industry and our hydrogen. These are examples of some of the users of that as straight CO2. So there is a fertilizer plant which currently, you know, is using natural gas and actually captures CO2 as part of its process. Today, it just releases it. That will just come straight into our network for storage. There's a big cement facility up there. We will be capturing from that. CO2 is an inevitable component of cement manufacture. You can fuel switch, but there is chemical arising CO2. We can put that in there. And also the cracker at the refinery, again, the CO2 can go in there. But actually what we're really here to talk about is the hydrogen production. So we are using UK technology, Johnson Matthey's technology, which is established technology. It's called an autothermal reforming system, and it allows very efficient capture, well, production of hydrogen and capture of CO2. So we will be capturing over 97% of the CO2 coming from the natural gas that will be going into that system. And as I said earlier, we're building a series of plants. The first one is 350 megawatts that will give us around 3 terawatt hours of hydrogen. So remember, we needed around 300 terawatt hours. Our first plant will give us 1% of that, and then rising to around 10% by the time we finish the facilities here. We're working with a big EPC contractor. We're currently doing the FEED engineering on that facility, and we are in partnership with the refinery up there to build the first 2 lines of that facility, operating the first one in 2025 and the next one following around a year later. That enables us to produce hydrogen, and to again give some numbers, we will be around 40-45 pounds a megawatt hour, and in Graham's numbers, that's I think around £1.60 a kilogram in terms of the type of cost that we're talking about. So considerably cheaper than we can do green today. I fully understand that by the time we get to 2040, 2050, it will be an absolute mix of the two, and there will be cases when green is the same or cheaper, but it allows us to start saving carbon today and grow at the speed we need to and at the cost we can afford. So this is the distribution system. This is the only UK cluster that is designed to link production, storage, and then the users. And we're partnered with Innovin, who currently, there are currently natural gas stores down in Cheshire salt caverns today. We will be storing in there, and the amount of hydrogen we'll store is 1 terawatt hour. So I think Graham talked about that very large flow battery he was working on, and that is a huge battery in battery terms. We will be storing 10,000 times more energy than could have been stored in that. So I agree with Graham, this is a great way of storing energy in order to deliver what we need in terms of reliable power. And then we're working with the industry in the region. We're working with around 30 industrials who have a real appetite to tackle their carbon issues through switching to hydrogen. So we've just done a big set of trials with a regional burner manufacturer operating a very large furnace of theirs, test facility of theirs, using hydrogen. demonstrated we can do it safely, emissions profiles and everything else are as we need. That is a precursor to 2 sets of trials we're doing. We're doing a trial at Pilkington's in the next couple of months, taking one of their big glass making furnaces, about 50 megawatts of capacity. So whatever that is, 3 orders of magnitude bigger than your domestic boiler at home. As part of the glass making process, we will be demonstrating running that on 100% hydrogen as well as a blend, and also working with Unilever that makes lots of the products that we have in our bathrooms and kitchens. Big steam raising boiler that they have, 7 megawatt boiler, typical of around 1,000 across the country. We'll be running that on 100% and on a blend as well. And this is about, yes, technical demonstration, but it's also about hearts and minds. Companies need to see that it is possible. It can happen in their types of industry and organizations that allows them then to have the confidence to make the switch when the hydrogen becomes available. So the other key area I'd like to cover before I finish is about blending into the gas grid. We see this as a key enabling step. So currently in the UK, you can only have 0.1% hydrogen in our natural gas. We have been doing the HyDeploy project that I'll tell you about, which is based on 20% by volume, I will say. So that is 6 to 7% by energy, can be safely blended into the gas grid. And the key things about that is it's non-disruptive for our users at home. So they get a mixture, they don't have to make any changes, but they are already seeing a reduction in their carbon intensity. If you do that across the country, it's actually quite significant. You end up saving around 6 million tons of carbon, which is equivalent of taking about 2.5 million cars off the roads. That allows us to build up hydrogen production capacity, green, blue, bio, that's got a market. It's established the key regulatory positions with the HSE. We build the supply chain. We help customers get used to hydrogen as part of their energy mix. And we unlock the use of hydrogen more widely, potentially 100% into the gas network. So we started a program that we started back in 2016 at Keele University. So it's the largest campus university in the UK. They own and operate their own gas network, and it's typical of a small town. So we wanted to use their network to establish that we can take a blend of hydrogen and natural gas, distribute it and use it safely and efficiently without any disruption. And you can see we've got partners here, Cadent, Northern Gas Network, ourselves, ITM Power, who provided the source of hydrogen for this, the Health and Safety Executive in terms of their science labs, and Keele University. And this was funded by Ofgem under their Network Innovation Programme. So this has been a very successful project. We spent 18 months making the safety case that it was just as safe for 20% volume hydrogen as natural gas. That is the first time in the UK that case has been made. It was equivalent to around 3 or 4 PhDs worth of material from fundamental gas characteristics, material science, operational procedures, appliance combustion and how it works across the whole system. We then built the facility, and you can see it here. And actually what you're looking at here in the foreground is actually is one of Graham's electrolyzers, which then made the hydrogen, which went into a small buffer tank before it was then blended into the gas system using that unit. We obviously engaged closely with all our consumers, and throughout that we had safe appliance operation, no increases in leaks or faults, and uniform network composition. We also took the chance to run not just into people's properties and into the 30 or so commercial buildings. We set up a test facility here, which you can see, with 2 boilers from each of the 4 UK manufacturers. They'd all stood behind their warranties for our customers during the trial. This was about accelerating testing. So we actually hung 2 boilers from each, one on natural gas, one on the blend, ran accelerated testing and ran them hard for the period of the trial. So they did the equivalent of 12 to 15 years worth of operation. Then we took them off the wall. We've sent them back to the manufacturers for them to strip down and then they have to tell us which boiler was on natural gas and which was on hydrogen, and whether they could tell any difference. So they've currently got them now. The trial just finished just after Easter, so they've got the boilers now, and we'll be getting the data from them. And overall, this was a great project because our customers loved the fact that they were saving carbon by actually not having to do anything. Where else do you get to do that? And then that's leading us on to our public network trial, which is about to start in around 6 weeks or so, up in Winlayton near Gateshead. So we will then be going into over 600 properties, and now we are on a public gas network system. We are finalising the safety case with the HSE, so we are awaiting their agreement to the case that we put. So obviously it is dependent on that. But once we have that, we've constructed the facility, we are ready to roll, and we will be able to start injecting into a public network for the first time ever in the UK. And we see this as an important part for our domestic heat, as a journey to potentially 100% conversion of the gas grid. You saw from that fluctuation in energy on the gas grid, we have no hope of delivering that fluctuation of heat using our existing electrical network. The gas network is perfect for doing that, taking that big volume swings and delivering the energy. Baxi, Worcester Bosch have developed hydrogen-ready boilers. You've probably heard about those in the news, even in the last couple of days. And that 10-point plan that Graham talked about calls for a hydrogen neighbourhood by 23, a village by 25, and a town by 2030, when then hopefully we can start to roll out chunks of conversion across the grid. Finally, before I close, I guess it's worth just saying not only is this about low carbon, and that's clearly what motivates us, but actually it really does underpin UK industry and safeguarding jobs. So we create huge swathes of jobs by doing this, but importantly, we also safeguard those existing ones. We create significant value to the UK and develop exportable skills. And we have a real leadership position in terms of our offshore and chemicals industry. And this allows us to grow and expand that and send it further around the globe, as well as in this region, the potential of saving around 10 million tonnes of CO2, not just from industry, but from our domestic transport and other sectors by 2030. So I would say, yes, we have a huge challenge. I think I painted that at the beginning, but there are ways to solve it. There are a suite of problems, of solutions, using a suite of individual technologies. But with this kind of configuration, this kind of infrastructure, we can reach into our industry, into our power sector, into our domestic sector, into our transport sector, and get us down to the net zero that we need to be. So I will stop sharing now, and I think we're about to go for some questions.
Indeed, thank you. Thank you both, Graham Cooley and Chris Manson-Whitton. Who would like to ask the first question? Perhaps you'd like to click on the reactions.
If you'd just like to click on the reactions and raise your hand. I guess while that's happening, I'll start off with a question, perhaps for you, Chris. As somebody who drives from the south of England to the north of Scotland on a regular basis, I haven't been sold an electric car yet. Should I keep my gas-guzzling Volvo XC90 going till I get my hydrogen car, or should I do something in between?
Well, I mean, I would say, in fact, Graham is the one that should probably answer this, because Graham is actually, has facilities or has provided electrolyzers in a number of filling stations up the country. So exactly where they should be. Yes, you can buy fuel cell vehicles today. The challenge is where can you fuel up? So if you're lucky and you live near one, then yes, it would be a very legitimate thing to do. Clearly, what you need to know is whether you've got the infrastructure. The idea is that at projects like ours in the Northwest, but no kidding, there are similar plans developing in Humberside, in Teesside, up in Acorn in Scotland. So hopefully we'll build the infrastructure that can connect things up, that you will be able to do it.
That's great. Lindsay Greer, can I ask you to unmute and come into the conversation?
Oh, thank you very much. I thank the engineers for this event. I'm here as an armourer, and I'm just going to ask a very general question, which is, I'll phrase it this way. How big is what I would call the Hindenburg problem? That the public thinks hydrogen and they think something will go disastrously wrong. I think you're going to be able to reassure me that the engineering problem is not severe. So maybe my question is more about public perception and getting around that, especially at the level of your own car, for example, being hydrogen powered.
Okay, I mean, if I kick off, but I'm sure Graham will have comments as well. But the reason I'll kick off is that, look, we've had 100 residents at Keele University we've had to engage with. And you know, we've got over 600 in our properties in the northeast that we've been working with. So absolutely engaging with consumers is really important. It is really interesting to see who consumers trust. And I have to say, we are very in the UK with the Health and Safety Executive is actually a very strongly trusted body. Also, our universities are strongly trusted bodies. So at Keele, we had that strong advantage. Yes, Zoe Robinson, one of the professors at Keele, has done some social science research in this area, if you wish to look it up and talk about it. Yes, people do talk about Hindenburg, but actually pretty quickly they move on from it. They see the advantages, they understand the context, and genuinely they see the benefits of being able to keep heating their homes really straightforwardly or driving their cars with significant range from a hydrogen solution. So Graham, go on, you must have comments.
That's okay, thanks. So Lindsay, thanks for the question. You've got a great memory. You know, the Hindenburg was 1937. So yeah, Lindsay, just as a bit of fun, can you give me another example of an unsafe hydrogen event since 1937?
I'm going to dodge the question by saying that I was thinking it was really a perceptual problem here, not a real problem at all.
I think that's exactly right. You know, first of all, the safety record of hydrogen is fantastic. Just think, we use 70 million tons a year. Most of it is in the hands of industrial clients, so obviously, but a huge volume, and it has an incredibly good safety record. If you think about it fundamentally, because it's the lightest gas, actually, if you breach a hydrogen tank, it's gone in seconds. So I'd certainly rather my 14-year-old daughter sat next to a hydrogen tank than next to an injection molded plastic tank full of a liquid fuel. And in fact, if you tried to get the safety case for a petrol vehicle today, you'd find it quite difficult. Yeah, I mean, I think it is a perception problem. I'm not quite sure why that particular piece of Pathé News footage stayed in people's memory for so long, really. But there we are. I mean, to answer your other colleague's question about having a hydrogen car, because you can charge at home, the UK government has put 30 times more money into the electric vehicle infrastructure than it is a hydrogen infrastructure. So they haven't been particularly technology agnostic. And in fact, you will find, if you've seen the announcements about eliminating the sale of new cars from 2030, you'll see that there's a huge investment going into plug-in infrastructure and not hydrogen for passenger cars. I think the strategy of hydrogen refueling will be focused on heavy vehicles that return to the same place to refuel. I mean, one of the things about buses, trucks and trains is that they always go back to the same place to refuel. And so you have a depot refueling model. So this is the first thing. Second thing is that with a heavy vehicle, you value payload. So I'll give you some advantages of why you use a hydrogen drivetrain. So the first one is decoupling weight and range, which is fundamentally important if you're doing a bus, a truck or a train. Because if you want to increase the range of a vehicle using a battery, you need more and more batteries. And as you put more and more batteries to increase range, you increase weight. Whereas with hydrogen, if you want to increase the range, you make the tank bigger. So you decouple the weight and the range with hydrogen. So that's the first point. Second point is is refueling times. Refueling times are very fast with hydrogen, and they're a lot longer with a plug-in vehicle. Now, the principle of hydrogen and you being able to refuel very quickly means it's easy to do on a forecourt. The refueling model with a forecourt, but if you think through plug-in electric vehicles, even if it takes you half an hour only, and that's really rapid for a plug-in electric vehicle, you're not going to have a forecourt anymore, are you? Because if you had a forecourt, a traditional forecourt, that's why you'll see now a massive reduction if you don't have hydrogen in the amount of petrol stations. It will only be in locations where you've got massive parking, so that you can reside for half an hour and recharge. So with a heavy vehicle, and you're doing a bus, for instance, you want to get in the energy in quickly. And you can do that better with an energy gas by pipe rather than by wire and compressor. So I think what you'll see is an emphasis on plug-in electric vehicles, smaller vehicles, and heavy industrial vehicles that return to base. You'll see that's where hydrogen will be targeted. So that's maybe a longer answer to your question than you expected. Maybe it's Led Zeppelin you're remembering and not the Hindenburg and Papillon.
That's Barry Brooks. You would like to unmute and join the conversation?
Actually, Peter, before you do that, just notice on the chat, there's a notice there, most people killed in the Hindenburg disaster died because it crashed, not because of the hydrogen.
Yeah, and the flames was the cloth burning, not the hydrogen. As soon as the shell was breached, the hydrogen was gone in less than a second.
If we jump Chris Elsden just now, and we'll come back to Barry.
Okay, yeah. Storage. I think Chris Manson-Whitton mentioned a terawatt hour of storage, but I'm just wondering what percentage of the demand is there storage capacity for? Because if we can't store the hydrogen, then we're going to need something else to back up the energy when it's not being generated, the hydrogen is not being generated.
Yeah. So again, I'll start on this one, but again, there's a role for I'm sure Graham will have comments on this. So fundamentally, natural gas does what we need it to do. And certainly historically, we used to have quite a lot of gas storage. Now, because of LNG and things like that, we've been able to move ourselves away from that. And we're also using line pack in our gas network to do that. So the storage I'm talking about is separate to that. So gas is a very good way of doing it. And of course, yeah, I mean, Rachel's made a very good point on the chat that 1 terawatt hour of storage is less than 1 day of electricity and 10 hours of gas use. Yeah, absolutely. I mean, the numbers are right. But actually, when you're dealing with it, what you're really trying to deal with is some of those intraday, the fluctuations that you get. And actually, you're not necessarily looking to say, I need to run for a huge long period of time. It is that you're covering that fluctuation. Now, again, this is where I'd say there is certainly a role for blue hydrogen in this mix, because first of all, yes, you can make the hydrogen, you can store it, but also you are making hydrogen from gas, which you have available as well. So actually, it's a mixture of utilizing the capacity. Do you manage the scale of your facilities, or do you have storage? So you can actually have a facility where you have excess capacity. The actual capital cost of a hydrogen production plant for either type actually is small compared with the fuel cost. So actually you can have bigger plants, not use them as much, but then have the capacity when you do it. I agree there is a challenge to some degree if all your electricity has come from renewables and then you're making only green hydrogen, then there is some more thought you need to do in exactly how much storage you need. But providing you've got a mix of the two, I'd just say the kind of quantities we can provide can be analogous to what we've had traditionally in the gas network.
So in practice, there will need to be quite a lot of hydrogen production capability that will have quite a low load factor. Is that correct?
Or could have a lower load factor, and that's a balance. Yeah.
Thank you.
Let's speed up a bit now so we can get some more questions in.
Barry,
Barry, can you now give us your question?
Can you hear me this time?
That's better.
Yes, we can.
All right, okay. Thank you very much, both speakers, for excellent presentations. And it's particularly nice to hear that this sort of new technology is actually happening all around us whilst we're talking about it. So it's great news on that. You also talked, I think, about us in effectively needing a mix of everything, a system of systems approach. Could you say a little bit more about how you see nuclear power fitting into that system of systems?
Do you want to take that, Chris, or do you want me to?
I feel I've spoken a lot, but I'm happy to. But if Graham, from your national power days, you've got views on nuclear, feel free to chip in.
Yeah, I have got some views on nuclear. So, I mean, it depends where you want to start. Look, what's good about nuclear and what's bad about nuclear? So what's good about nuclear is that you can decarbonize the base load. And also nuclear is a steam cycle, so it gives you a lot of inertia. So your power system needs inertia, and also the power system needs a method of base load generation of low carbon energy. What's difficult about nuclear? The cost. If you look at the cost of renewable power now, and you look at the cost of renewable power and adding demand side balancing or energy storage, you find that it's pretty out of market. 9.6 pence per kilowatt hour versus Dogger Bank coming in at the CFD just under 4p. At that 9.6p that we were told was a fantastic price, however long it was, 6 or 8 years ago or something, looks pretty bad now. You know, there are trade-offs between the two. I've never been a particular fan of nuclear, but it reduces the challenges of running a balanced energy system. So there are good things and bad things. Nuclear waste is clearly another very bad thing that we need to sort out. I would appreciate it if the UK didn't spend its time getting revenue from cleaning other countries' waste as well. So I think there's a generational problem with nuclear. But the biggest one, to be quite honest, the biggest one for me is the cost. It's now out of market. And if you can use green hydrogen for long-term energy storage, and you use low-cost renewable power, and it gets you to net zero without using nuclear, and you can balance that energy system, then my preference would be not to use it.
Thank you, Graham. Actually, we've got a meeting in a few months' time on nuclear, on SMR, so that will come up and raised again.
Ian Gray, would you like to come in? Welcome, Ian. Good to see another Aberdeen man on the call.
Thank you. Thanks for the speakers. It was very inspiring. I'm going to ask just a question from an aviation sector point of view. Aviation didn't feature particularly strongly in your presentations as a use case, but there is significant work being put in across Europe, particularly through the likes of Airbus, looking at hydrogen from a fuel point of view. I'd welcome just the views of Graham and Chris around aviation and where you would see that fitting in terms of priority in terms of hydrogen production use cases.
Sure. So if I can kick off. By the way, nice to see you again, Ian. And when you were at the TSB, of course, you were the one who funded all of our early projects. So we have a debt to your fantastic organisation back then. What would I say about aviation? I mean, sustainable aviation fuel is a very interesting area. I think if you make it properly, in other words, you take CO2 from the atmosphere and you make it with green hydrogen, then you make a net zero fuel. We are making aviation fuel with Shell in Cologne. That's our 100 megawatt project. I was disappointed, by the way, that Shell canned its project with Velocys in Humberside. Thought that was a good project for sustainable aviation fuel. I think your initiatives with Zero Avia are very, very important. and inspiring. I guess the question is, will aviation use hydrogen, and in what form? Or will it use a sustainable aviation fuel like synthetic kerosene? I think if you use synthetic kerosene, then you have less technological change to the aircraft. Whereas if you use hydrogen, you need an electric drivetrain, and you need a combination of energy storage systems, like a fuel cell electric vehicle uses a supercat, battery for regenerative braking, and a fuel cell in the tank. You've got more work to do in looking at the drivetrain and the control system. So what's my prediction? Actually, in the early days, I think sustainable aviation fuel is probably the way that everybody will go, because there's less change to the vehicle. But ultimately, if you want zero emission at the point of the vehicle as well, you're going to need to move to hydrogen. I don't rate liquid hydrogen on board an aircraft, personally. I don't know what your view is. I think you obviously by now know a lot more about the space than I do, but compressed hydrogen and fuel cells look like a good option long term for me. Does that answer your question?
Yeah, no, thanks, Graham. It does. We'll have a separate conversation maybe at some point about the liquid hydrogen aspect. That's an interesting debate.
Yeah,
thank you.
Thank you. I mean, just
so two
on
questions from the chat. First of all, from Neil Glover, the Victorians operated town gas pipelines for many years. Town gas was about 50% hydrogen. Comment.
Yeah, I would make an observation that it is helpful, because it has provided some precedent for us. I guess a couple of things I would observe. First of all, in those days, our use of gas was much less sophisticated, so it was helpful. But actually, our boilers nowadays are much more sophisticated than they were those days. So your kind of ability just to say, well, it was fine before, it'll be fine now, isn't quite the same. So that hence, we've ended up with a case at 20% as a blend rather than 100%. Also, there are some beneficial aspects of the CO that was also in there. I mean, horrendous aspects in terms of safety, but as far as materials are concerned, there are some advantages in having CO and hydrogen at the same time. So useful, but I wouldn't say it's game changing in terms of making the safety case. It's just part of the story. Yeah.
Thank you very much. Anything more from Graham on that?
No, that was a good answer. I was going to mention the CO2 as well.
Well, there's a CO2 question, another question. What happens to CO2 in storage? Is it used for something else eventually? I think not. Any further comment?
So again, I guess what I'd say here is it's back to my charts trying to give some orders of magnitude. So there will be a role for CO2 reuse. I have no problem with that. And Graham's talked about whether there are some roles for sustainable aviation or fuels where you need carbon in them. I mean, we really want to get the carbon out, but in some cases it makes sense. I think if you look at the orders of magnitude, we need storage far more than we could reuse CO2. I mean, let's face it, that carbon sat in geological formations as natural gas for millennia. Effectively, we want to put the carbon back into those places to store it for millennia, would be my observation against that.
Yeah, I agree with that. I mean, when I was talking about sustainable aviation fuel, you do need a carbon molecule. I was not talking about reusing sequestered CO2. I was talking about the requirement that it will definitely happen for the world to need to remove some of the CO2 which is in the atmosphere. And actually, all you do when you make a sustainable aviation fuel is you borrow the CO2 for a short period of time. Because what you do is you take a carbon molecule, CO2 molecule, you attach a hydrogen molecule to it, and you use it as a fuel, and you re-release the CO2. So the carbon molecule acts like a shuttle. You stick it onto the hydrogen molecule, and then it comes out again. I mean, we are going to have to absorb CO2 from the atmosphere and sequester it. And there's one technology that works really well. Actually, I only know of one technology, removing CO2 from the atmosphere and sequestering it well, and that is a tree.
Thank you, Graham. There's one other question here we're trying to do. What water sources are suitable for electrolysis?
Sorry, say that again?
What water sources? Any constraint on the water you can use?
Yeah, you need clean water. There are a lot of, you can use nearly any source of clean water. I mean, we use obviously tap water all the time, but brackish water, you can use seawater with desalination. I mean, we have a project called Oyster, which is joint with Ørsted and Siemens Gamesa. And that project is looking at integrating wind turbines with and desalination equipment with electrolysis to make a full energy system, which is integrated together. So yeah, you can use seawater or any other form of water.
Neil Glover, you've got a question. Please join in.
I think we've had Neil's question already, haven't we?
No, this is a different one.
But Neil, I'm sorry, we've got somebody else who's had a question in the chat I want to take first.
Okay.
Michael Manelli's question, worth a 30-second share. There's safety skeptics as a wrote. It's back in 2001. Dr. Michael Swain with the University of Miami at Coral Gables attempted to simulate two car fires, one created by a 1/16-inch puncture in a gasoline fuel line, the other by a leaking hydrogen connector. Any comment on that?
Master, it was just merely to point out that that sometimes the public really don't see the other films, the Hindenburg, which I dug into quite deeply when I was at Farnborough in the 90s, the disaster and some of the speculation about it in many of the archives. But I really wish we could get some of these comparative videos out, and it's a short one worth viewing. Thank you.
Yeah, I know the video on YouTube. There's a natural gas and a hydrogen one, and there's also a gasoline one, isn't there? And they're good. They're worth watching. I agree. Chris, have you seen those?
Yeah, absolutely. They're very classic, and it shows what happens to the flame in one. You know, the hydrogen just gone. The gasoline, it makes you slightly frightened to sit above a fuel tank, as you said earlier.
Thank you. Neil, your question now.
Yes, it goes back to the battery electric vehicles. I can see 10 reasons for not getting a BEV, but I'm not going to list those reasons here. But the ITM fuel stations that they've done with Shell, I've been to the one at Cobham, but there's also the one at Beaconsfield, which looks very good. One of the things I see as a problem there is that you're generating the hydrogen from electricity from the grid. So what's the impact going to be on the grid if we're transporting electricity to fuel cars, whether it be battery or not? Are we going to have to increase the size of the grid, but electrical grid by a lot? Or should we be looking at distributing hydrogen in a different way? We've already seen Peter's put up a picture of a road tanker. Should we be taking hydrogen out of the gas network and compressing it, or what are your comments on that? And yeah. I've got a final point to come back later on offshore.
Thank you.
Yeah.
We're nearly out of time, Neil. Sorry.
Oh, okay. So if you make electrolytic hydrogen, in general, you're plugging into the high voltage network. If you plug in an electric vehicle, you're plugging into the low voltage network. The low voltage network is the one that is under capacity. And if you were to reinforce it, you have to dig up the roads. Whereas the high voltage network, not only is it high capacity and easier to reinforce, but it's the one where you need to a grid balance for frequency. So I don't know where you are in terms of your understanding of grid balancing, but on the high voltage network, on the transmission system, grid balancing is all about regulating frequencies. And what you do with an electrolyzer, of course, is you run it and you can turn it on and off very, very rapidly. So you allow for demand side grid balancing, and you can do primary grid balancing because you can turn it on and off in less than a second. So that gives you a flexibility advantage on the network. So you don't actually look at balancing frequency on the distribution network. Actually, what you need is voltage stabilization on on the electricity distribution network. So there's an advantage in having a fleet of flexible loads on the transmission network in terms of balancing frequency. Will you need a lot of electricity? Yes, you will. You will need a lot of electricity, and I think electrolytic hydrogen, of course, uses electricity, renewable power, to produce a gas, a fuel, but it is a net zero fuel. So it gives you some significant advantages when you have more and more renewables on the network. I'll give you a nice example. An example of falling frequency. As you know, as the frequency goes down, that's because the network is overloaded, and you can turn the electrolyzers off. Actually, as the frequency goes up, what it's not, nearly every event of rising frequency is when you get an excess of renewable power hitting the network. Because of course, wind power doesn't have much inertia associated with it. And that's when you need to turn on to balance rising frequency. So actually what you have is a signal that comes from the network that tells you rising frequency means you've got excess renewable power. And that's when you turn the electrolyzers on to balance the grid and absorb the excess renewables and make green hydrogen. So it's a study we did with National Grid, with the electricity transmission part of National Grid, as opposed to the gas distribution part of National Grid, which is now called Cadent.
Okay.
Thank you.
Thank you. I'll leave it there.
Okay. Chris, any further comments from you?
All I'd say is pipelines are also a good way of getting hydrogen around. They're good at doing that. So you're not just having to produce locally. You can use pipelines to distribute. Yes, they will need a very small polish at the end before you can put it into a fuel cell, but that is doable too.
Oh, can I just comment?
No, sorry. No, Neil.
The pressure on the pipeline is much lower than is required for the vehicle, so you still then got to compress it.
You will need some compression, yeah.
Thank you very much. Well, this has been a fascinating event. I think our thanks, if we could all unmute ourselves, our thanks to our two speakers, Chris and Graham. Unmute everybody. Thank you very much indeed.